Welcome to Unit 5. In Unit 5 we are going to look at nuclear energy, and we're going to begin by looking at how nuclear energy works. So recall when you burn a fossil fuel that you take a solid and you convert it to things like ash and gas and liquid. But if it starts out carbon, it ends up carbon. There's no atomic change. For a nuclear reaction, you're causing a change at the atomic level. So let's go back and look at the structure of an atom. In the nucleus, we have neutrons and protons. Neutrons are particles with mass but no charge, and protons are particles with positive charge. Remember, the number of protons determines what type of atom it is. On the outside of the nucleus, we have the electrons. Those are negatively charged particles. There are two types of nuclear reactions. Fission: you take a large atom and you split it into smaller atoms. So if you look at the example over here, we start with an isotope of uranium, uranium-235, and it splits into two different atoms. Typically these are radioactive as well. You also get some neutrons out and energy. The other type of nuclear reaction is fusion, in which case you take two small atoms and combine them to get one larger atom of a different type. So we have here hydrogen 2 and hydrogen 3 being fused into helium, and you end up with a free neutron and energy. We can do fission here on Earth. We cannot do fusion. Fusion at the moment really only happens in stars and places like that. Okay. Both release a tremendous amount of energy. If you look at fusion, you can take two hydrogen atoms. So deuterium and tritium are both hydrogen atoms. They differ by the number of neutrons in the nucleus. You get out helium, energy, and a neutron. This occurs, as I said, in stars like the sun. It takes temperatures of 100 million degrees and tons of pressure, so billions of atmospheres of pressure, to cause fusion of deuterium and tritium. You are converting mass into energy. Lovely. So now let's look at fission, and to look at fission we need to talk about isotopes. So isotopes are different forms of the same element. So they have the same number of protons but different numbers of neutrons. Tritium and deuterium were isotopes of hydrogen. Right? So U-238 has 92 protons and 146 neutrons. It's a stable isotope. More than 99% of the natural uranium on the planet is U-238, as opposed to U-235, which has 92 protons but only 143 neutrons. It is highly unstable and accounts for less than 1% of the naturally occurring uranium. When you split uranium, you release a ton of energy. Only uranium-235 is usable in fission. If you hit the nucleus of U-235 with a neutron, it splits. Right? In the example shown here, we take a neutron. Here's our uranium nucleus. Here is the fission process, and we have a isotope of strontium and an isotope of Xc, I believe that's xenon, released, and a bunch of neutrons. So we have to make fuel. The first thing we need to do is mine some uranium. We then take out the U-235 that we need. This is the enrichment process. You need a 3% concentration for nuclear energy. And then you take fuel rods where you stack 1.5 centimeter pellets of the uranium together to create the fuel rod, and then the fuel rods are assembled further to create the actual fuel assembly for the reactor. Right? An 8.5 gram pellet of uranium is equivalent to 1 ton of coal or 4 barrels of oil. That's pretty impressive. 8.5 grams is equivalent to 1 ton, energy production wise. Right? 1 kilogram of uranium releases the energy required for a nuclear bomb. Here, we're going to look at how nuclear reactors work. As we just said, we take the pellets, we stack them into metal rods. Those rods are 4 meters long. 100 rods put together is the fuel assembly. 1,000 fuel assemblies are bundled into the reactor core. This is 100 tons of uranium-235. So when you strike the uranium nucleus with a neutron, nuclear fission occurs. And because when the nucleus splits, it releases more neutrons, you get a chain reaction. The neutrons generated from this splitting go off to cause more splitting. Here is a picture of a nuclear reactor core. It is blue because it is underwater, but you can see how it is glowing. Okay, well, I split this uranium nucleus. I get neutrons out. Those go off and split more nuclei, creating more neutrons, and so on and so forth. If you do not control this process, it escalates big time and leads to an explosion or a meltdown of the reactor. Right? So we have to put something in the reactor to slow the reaction. Typically those are these neutron absorbing materials, control rods. Typically they're calcium or boron. Right? So not all of the neutrons that are released make it through the control rods, therefore not all the neutrons can cause a additional fission event. It's all in water, as we saw in the last picture. And the reason it's all in water is because you circulate the water to remove the heat, to remove the energy. You want to keep this thing nice and cool. If you look at a nuclear reactor, you have these dome structures. These are where the nuclear reaction takes place. Right. So you have a superheated core inside where the reactor rods are. That superheated water is pumped out to a steam generator. Then used to heat secondary water. And the reason we do this is because the water that is in the core is radioactive. So we want two separate closed systems. The secondary water, once it's heated, is actually piped to the turbine, which is turned to create energy, just like in the coal power plants that we saw a couple units ago. There's then a cooling tank to convert the steam back to water, and it's recirculated. Here is a picture of that. The pink here shows the water in the reactor system. It's heated. Over here it passes through the secondary water system and converted into steam, which turns the turbine. Here is the cooling system, and there is the cooling tower, what we typically think of as that's part of the nuclear reactor. As we saw, those also are at all types of reactors, whether they're, or power plants, I guess I should say instead of reactors.